Well, hello, everybody. This is a 3D view looking east and down at summit bathymetry and topography of the Woodlark Basin here in the middle in blue, being subducted under the Solomon Islands in the Southwest Pacific. So here's Australia. We're at this little piece east of New Guinea. And the subject of today's webinar is the Itina Trough, which is this feature here that's 5.4 kilometers deep, that I named after a river that drains southwest Guadalcanal. It has had a checkered history, first thought to be a fracture zone, then for 50 years considered to be the eastern continuation of a fossil trench, but this Bucklington Trough is only 4 kilometers deep, until my paper in 2021 that showed it is a young rift. So let's take a look at that. Here are the four figures that were in the 21 paper. And swath bathymetry showed that the Itina Trough is much deeper and diagonally truncates the Bucklington Trough. So here's the Bucklington Trough, comes around, and then this thing cuts right across it. And it has a typical zigzag shape of a rift graben. So the Bucklington Trough is indeed a fossil trench, and this was a remnant arc, as Dan Carrig showed in this seismic profile from 1972. And Jacques Récy published a similar profile across the Reynolds Trough and Ridge a few years later, again, a remnant arc trench system. But in between, in 73, Bruce Lyndike, Ken McDonald, and others published this profile across what I now call the Itina Trough. And it had a very different aspect. It has very steep sides. There are true dips of 30 degrees. It's not asymmetric in the same way that these trench systems were. And so something different was going on. Now, stepping back and looking regionally, this set of blue lines are a series of former subduction zones where rifted fragments from Australia and the ocean seaward of them were being subducted in the Paleogene to the northeast. And there was various collisions, the Papillon Plateau, the Louisiade Plateau, the Norfolk Ridge, and things into this system that sutured them. But they were the Paleogene trench, and associated with that on Papillon Peninsula and in New Caledonia and in Northland, New Zealand, were in place three large arc-ophiolites. So that's the regional setting, and indeed, notwithstanding this profile from Bruce Lyndike, the interpretation for the last 50 years has been that this was indeed an arc trench system, and without knowing the details of the Itina Trough, that it was just the continuation of this Bucklington Trough all the way into the current trench axis. And that's what prevailed. Now, we all forgot or didn't know about the 1961 survey by Dale Krause for cable and wireless of telecom cable routes in the Southwest Pacific. In fact, Dale Krause was the one who named the Bucklington Trough after the reef and the Woodlark Basin and many other features in the Southwest Pacific. And he, in a report that came out in '67, recognized that this thing with east-west trend and much deeper than the Bucklington Trough was a separate thing, which he called the Bucklington Fault. So he also had a fracture zone interpretation influenced by Sam Carey for this feature, but he did realize that it wasn't the same thing as the Itina Trough. And then eventually I came along a couple of years back and inferred that this was a rift graben that cut across this thing. So here is a detail of that to show two things. The first is we didn't have enough time actually to survey the very southern ridge of this system, but you can see in the vertical gravity gradient that it is a continuous feature, even though the swath bathymetry doesn't capture it all except on the ends of some turns. The other thing that this picture shows is that at intermediate spreading rates, which are relevant here, the continent ocean boundary is a boundary. It's not a transition. It's a boundary as sharp as any other plate boundary, whether it be a pseudofold or a fracture zone or a transform fold or a spreading center or a trench axis. The continent ocean boundary is incredibly sharp. Now, we'll see later, one of the important features of this basin is that this area, the easternmost area of the basin, has a fabric which is not copolar with the rest of the basin to the west, which opened around a pole near Port Moresby. And that will become important in the next bit of the story. So anyway, here's this thing, this 5.4 kilometer deep with 30-degree slope on the south. And the oldest part of the basin is just here. It's about 6 to 6.2 million years old. As Gary knows from ODP drilling and commercial drilling at the western apex of the basin, the rift onset unconformity is 8.4 million years old. So in 21 paper, I interpreted this as a rift graben at the very beginning of opening of the Woodlark Basin about 8 million years ago. Then in 2022, the next year, Anders McCarthy published this profile on the bottom of a Ewing 95 multi-channel seismic line that they reprocessed, which is this line shown here in white, which goes from the Louisiade Plateau with its 30-degree southern slope and ridge across the Itina Trough, which they didn't call it because they didn't know about my paper yet, over the rifted eastern Pollington Rise, and then into the trench underneath Guadalcanal. Now, this is their line drawing on top of that seismic section. But they also reported dredging this corner of the southern scarp and recovering serpentinized peridotite, mid-ocean ridge basalt, and volcaniclastic breccias and conglomerates, which they inferred was the equivalent of the Papillon ultramafic belt that was in place on the Papillon Peninsula to the west. So again, further corroboration of the idea that this Louisiade Plateau, this Australian microcontinent, had collided with a former arc trench system and sutured it, but then this thing got ripped apart to form the Itina Trough. Meanwhile, a PhD student of mine, Elizabeth Benechek, was doing a very detailed reconstruction of the opening history of the Woodlark Basin. And this and the next few slides are from that paper, which is in review in GQ. So west of this feature called the Simbo fracture zone, all of the abyssal hills and the magnetic lineations form about a pole prior to the very recent reorientation of the spreading axis that was around Port Moresby. So they're all copolar to the west, and the fracture zones are concave to the west. But that doesn't work for the easternmost part of the basin. And in fact, you can see here, blown up in the bottom right, this is the bathymetry, slope, and magnetization. The Renonga fracture zone, transform and fracture zone, is concave to the east. And the opening pole for that area is actually over here south of Santa Isabel.
Il y aura 10 minutes.
Thanks, Gwen. So this became a multi-plate issue, And Elizabeth realized that if you opened this Itina Trough later than 8 million years, in fact, she posits between 1 and 2.6 million years, about a pole here. If you close this up, you can actually get this fabric, the older than 2.6 million year old part of the crust, to be copolar with the rest, the older part of the basin to the west. So that's the interpretation I'm going to show you next, where we dissect the Woodlark Basin opening into several different plates and microplates because of the evidence that we see in the easternmost part of the basin. So here is the magnetization on the top and the bathymetry on the bottom with the major tectonic boundaries, the brunes between these black lines, including up here near Simbo, the Ranonga Transform Fault concave to the east, all these other transform faults and fracture zones concave to the west. And the magnetic anomalies, here's anomaly 2 to Jaramillo, being about a pole to the east, even as we posit that this Itina Trough opened around a local pole to the west. And we've actually got a movie in 0.1 million year time steps of the whole 6 million year history of the basin. I'm just going to show you one slide of part of that reconstruction and what happens when, as I said, we have 0.1 time steps. But this thing in dashed red line is the posited Gizo microplate that was rotating counterclockwise between 1.2 and 2.6 million years, so that before that, the Itina Trough was closed. And then starting from 2.6 through 2 to 1, this thing opened, and here it is today. That's the bathymetry, and you can see the same over in the magnetics. So in this scenario, it's even younger than the 8 million years that I had originally posited, and helped the Gizo microplate rotate to have the spreading center more orthogonal to the trench, which for some reason ridge subduction likes to do. So back to our beginning slide. This then is the overall picture for the Itina Trough, first thought to be a fracture zone, then the continuation of this fossil trench, but in fact a very young rift, and even younger than I had first thought, formed during the opening of the Woodlark Basin. Thank you very much.
Thank you, Brian. I forgot to say to the audience, if you have questions, you can raise your hand or you can write the question in the chat if you want. I found it very interesting. I have a first question. When we are talking about reactivations like that, often we like to bring on the table either the thermal influence or the structural influence. But in your case, what are your thoughts on that? That even though we have that oceanic basin there already in place, we still need to accommodate just on the side, creating a new rift. I mean, at the plate scale, that's quite, it's a very narrow setting.
Yes, and it's even worse than that, because what it does in terms of inherited structure, it actually rifts across the former suture between the microcontinent and one half of the remnant arc was once, you can't see my hands, was once together. The Woodlark Rise on the north and the Pocklington Rise used to be together before the opening of the basin. That one remnant arc was collided with the Louisiana Plateau, and it cuts across that suture.
Do we have any idea of the crystal thickness?
I have one more slide. So at 2.6 million years, this is 0, 2.6, 5.2 of the whole region. And we don't know what happens further east because it gets inducted. But this is when the young basin starts to interact with the trench. And it doesn't like and it sort of tries to get itself out of the way and whatever. But it does not simply. I mean, later on, you can see this reorientation of the axis, which also happened here south of Simbo. But this actually rips a piece off. And it rips off, and even though this is young lithosphere, this is only 6 million year old lithosphere, it rips off the continental edge. And I won't pretend to know how the mechanics of that work. I think the only other modern example of rifting across a suture would be the Gulf of Corinth in the Hellenides. But it's very different here. And it's about reef subduction and interaction with the Solomon Islands. And I'm waving my hands because I don't have a mechanical answer. I'm just describing what I think happens.
Oh yeah, that's very interesting. Just rapidly, we have Derek. You had the question, Derek, first?
Yeah, is the Itina Trough still active, or was it deactivated with the bridge?
No, we know definitively that it's not active. I've got a paper that just came out in GCube this month, in fact, January, on the Solomon Island subduction, and you can look in there and see the seismicity for the last 100 years. There are normal fault earthquakes that trend east-west right at the intersection of the trough with the trench, as there are with the Woodlark Rise with the New Britain Trench. But there's no seismicity on the main part of the Itina Trough.
Okay. Ola?
Yeah, so you already answered one of my questions, which is exactly what Derek asked, if it's still active. So since you say that there's no seismicity along it, which I think it's a really important indicator of activity, what do you think caused the failure of the incipient rift?
I think you're repeating Gwen's question.
Oh, okay. Probably missed that.
To which I didn't have a good answer. I still don't. I do know from looking at the rifting of the Woodlark Basin to the west into Papua New Guinea, that always, every time the rift approaches the older Solomon Sea Basin, it jumps away into the continent. So the continent is clearly, on the north you have the Solomon Sea, on the south you have the Coral Sea. Those Paleogene ocean basins, lithosphere, is clearly stronger than the Papuan Peninsula and the remnant arcs. But in this case, you're looking at a very young ocean lithosphere compared to the continental Australia remnant arc. And why that suture is weaker than the young lithosphere is an enigma to me. And you can see very clearly here, it cuts right across that paleo trench and suture. I mean, it just diagonally truncates it. It's a knife edge. It's remarkable.
But if the crystal thickness is still big enough, you may still have some significant ductile material within your bicontinent.
The plateau goes underneath this trench. But what I'm saying is where this rift happens,
right,
goes right across that thing diagonally. It does not simply follow even the former trench axis.
Yeah.